Hello, we're now on part 3 of chapter 4, and we will put together how pressure gradients, Coriolis force, and friction effectively produce and influence surface and upper level winds, which we will call geostrophic. Upper level winds and surface winds simply behave differently because not all three forces are necessarily present to the same degrees. So basically we compare the pressure gradient to like the gas pedal on the car, which gets your car to go forward. That's what creates wind. Steering wheels are sort of like the Coriolis force that kind of control direction, and we know Coriolis force wants to move winds to the right. And then we have surface frictions, which are like the brakes, which try to slow down wind. When we talk about upper level winds, geostrophic winds really only have pressure gradient and Coriolis force. Once you get above the Earth's surface a certain altitude, you no longer deal with the influence of trees and buildings and mountain ranges that are effectively slowing winds moving across the pressure gradient, and as a result, the winds are no longer being influenced by friction, and we call this geostrophic airflow. And upper level winds simply move and behave differently than surface winds because they only have two of the three forces affecting the wind. So we move to the next slide here. And when you see the next slide is we have a pressure gradient driving, which PGF stands for pressure gradient force, driving winds to move from south to north. And effectively, what begins to happen, though, in the upper level atmosphere is we could have a pressure gradient moving the winds south to north down the gradient. However, because of the Earth's rotation, we would eventually see the winds move to the right in the upper atmosphere, balanced by the Coriolis force. So the Coriolis force over the United States could actually take a southerly wind trying to move across the pressure gradient to the north, and ultimately in the upper atmosphere the winds will start to move parallel to the pressure gradient itself. And this is exactly the way it would look in the upper atmosphere. We could have high pressure to the south, low pressure to the north. The pressure gradient says move across the pressure gradient from south to north, and geostrophic airflow occurs when the upper level winds move then across and deflect to the right across the pressure gradient, and so that southerly wind then becomes a westerly wind moving to the east. And these winds simply are identified because winds typically move parallel to the pressure gradient, and geostrophic winds often are very strong because there's no friction to slow them down. This is why upper level winds are often very strong, are much stronger than surface winds, because they don't deal with the force of friction slowing winds across the pressure gradient. We call this geostrophic airflow, and in particular we look at how winds are moving around, in particular upper level features like ridges and troughs. And so when I show you some upper level wind charts, we see this, what we call gradient flow, and I'm going to kind of go to it right now to move it along. Around highs, we see the ultimate pressure gradient is moving parallel with the pressure gradient itself across or with the isobars. If you'll notice, the purple arrows indicate the airflow, and it's moving in a clockwise direction around the high, and the pressure gradient to the with the low is moving around a low counterclockwise, and the air is moving when the purple arrows, and if you'll notice, the air is moving parallel. It's not moving across the pressure gradient, it's moving with the pressure gradient. So this geostrophic airflow, these winds typically are moving very much stronger than surface winds, and these upper level winds are also moving a little differently. So I typically call geostrophic winds are kind of like cheetahs, whereas surface winds tend to be like lions. Lions are bigger and they have the ability to, they're much stronger animals, but they don't have the speed. And upper level winds tend to move much faster than surface winds, like a cheetah is much faster than a lion. And so one of the more famous upper level winds we'll be talking about later is called the jet stream in chapter 8, and it'll be very easy to identify it because it's such a fast moving wind. It typically stands out in regard to other winds around it. This is what upper level winds look like flowing across the atmosphere, and we're talking now about 15 to 20,000 feet in altitude, we could see we could have a pressure gradient pushing winds to the north. And this feature here is a ridge, and when we see pressure lines moving to the south over the eastern United States, this is called a trough. Ridges are usually identified with pockets of warm air pushing north, and troughs are identified as really pockets of cold air pushing south. They're really redistributing cold and warm air over the United States. The pressure gradient overall is south to north, but as the winds are then deflected to their right because of the Coriolis deflection, you can see the airflow produces like a river of air moving from west to east. And this is very typical of the airflow over the United States and the upper atmosphere, is we do have a west to east airflow, and it's the identification of these ridges and troughs that tell us if we're going to be unusually warm or unusually cold that day, because this really represents, ridges are representing warm expanding air coming out of the south pushing north, and troughs are identified as cold air compressing air pressure lines to the south. So right now the eastern United States is under a trough, and then the western United States is under a ridge, and this would have pretty significant impacts on why the western United States is under unusually warm air and the eastern United States is under unusually cooler air. When we start talking about surface winds, though, we start dealing with different terminology, and the winds do move differently, and there's certain behavior that we want to identify. Cyclones and anticyclones refer to surface highs and lows. Troughs and ridges really refer to upper level highs and lows. And when we talk about surface winds, we talk about high pressure systems are called anticyclones, and low pressure systems are called cyclones, and they have very specific motions and weather associated with each, and they're identified here with very short and tight text in terms of what is the associated wind movements and weather associated with each. And I'm going to talk about each one here quickly, but I can't stress enough, looking at the videos I have placed under Chapter 4 about air movement around anticyclones and cyclones would be very valuable for you to look at, or just Googling airflow around anticyclones and airflow associated with cyclones, and actually seeing visuals. I know there's plenty of good YouTube videos that really talk about. So if I wanted to study low pressure airflow, would be a search string in YouTube that I would want to put in if I wanted more visual examples of what I'm about ready to talk about. So I'm going to move forward here, and we're going to talk about the weather associated with each and the airflow. Basically, surface winds have to deal with the added factor of friction. And when you basically look at it, when you have surface winds, you've got pressure gradient moving one way, which is to push air from high to low. Pressure or Coriolis force wants the air to take a hard turn to the right, and surface friction wants the wind to actually stop. So it's actually, I wish there was an F here pointing the opposite direction as the pressure gradient force, because friction wants to basically stop pressure gradient. So effectively, surface winds have three forces. So what we end up seeing is that with surface winds, we actually get a wind that is a combination of all three. The net effect is Coriolis force weakens as air slows down, and surface friction working against pressure gradient causes surface winds to deflect. So with geostrophic winds, the winds end up moving parallel to the pressure gradient identified by the isobars here in white. Surface winds end up moving across the pressure gradient. They can't make a hard turn to the right in the northern hemisphere, and notice this would be an example of a southern hemispheric wind because it would deflect to its left. That a surface wind tends to blow across the pressure gradient to its right in the northern hemisphere. So it's sort of an accommodation of all three, and because Coriolis force is not working as strong because winds are slowing down at the surface, the winds don't take a hard turn to the right. They take about a 30-degree turn to the right. And in the southern hemisphere, they take a 30-degree turn to the left. And so winds blow across the pressure gradient at about a 30-degree angle. So that's why when we look at surface winds, we see the winds moving across the isobars instead of moving with them parallel. So this chart cannot be underestimated enough for understanding the weather associated with highs and lows. This is an example of a northern hemispheric high or anticyclone. Air is being pushed out across the pressure gradient. As the air pressure is highest in the middle and lowest towards the outside, the wind rotates out to the right, spiraling outwards counterclockwise. If this was an upper level high, we would see the winds moving with the pressure gradient, and the winds would be moving parallel to the pressure gradient around the isobars or the pressure surface. These winds would probably be weaker than the geostrophic winds, as an upper level high wouldn't have to deal with friction. The bottom two examples moving to the left would be examples of high pressure systems moving in the southern hemisphere. Low pressure systems are examples of the air reduces an air pressure towards the middle, so the air is getting pulled in, and the air is getting pulled in counterclockwise, and it is deflecting to its right to the pressure gradient, and the air is getting pulled in counterclockwise inwards. The same process occurring with an upper level low, but it is rotating around the low, and the air pressure is moving perpendicular, not perpendicular, but parallel to the pressure gradient. And we can see the airflow is rotating opposite to the left in the southern hemisphere. Now, in particular, what we want to understand is what is happening three-dimensionally as air is being pulled into a low. The air is also rising, whereas with a high, as the air is being pulled out, it is sinking. And this has major influences on whether or not we see with anticyclones clear skies, and with cyclones we see cloudy skies and often rain associated with it. So we'll come to that here in a second in terms of how vertical air motions are associated with that. In the upper atmosphere, we tend to see pressure lines identified with features called ridges and troughs. A trough is an area in the upper atmosphere where cold air is pushing south, and we see our pressure lines moving southward, indicating cold air moving in from Canada over the United States. Ridges are associated with warm air expanding and pushing into the north, and that usually brings warmer air out of the south and Gulf of Mexico into the United States. This airflow in the upper atmosphere will become essential to understanding severe weather and weather forecasting in later units, but these ridges and troughs are absolutely critical for us to understand because our surface highs and lows are connected three-dimensionally with what's going on with the winds moving above the Earth as well. So we end up looking at maps like this, and we try to identify patterns of highs and lows over the Earth. This is an upper level map. This is more of a surface map. The higher or the lower the number becomes, the more higher you're moving up into the atmosphere. So a 300 millibar map is higher up in the atmosphere, maybe 20 to 30,000 feet in altitude, whereas an 850 millibar map is maybe 1,000 feet above the Earth's surface potentially. And so these maps are giving us an idea of how the winds are moving at different atmospheric altitudes. This would be more of an upper level map, and this would be what a pilot would look at. And obviously there's a big trough over the eastern United States and a big ridge in the upper atmosphere over the western United States, and we'll get more details about the kind of weather we would associate with these features. And in the eastern United, or in this map A over here, this would be maps that would be more influential for if we were trying to understand how winds were moving closer to the ground. So when we measure wind speeds, we often measure wind speeds based upon what direction they come from. And when we look at wind speeds, we often talk about air moving from the direction it's coming from as identifying and labeling its wind. So we use wind vanes and anemometers to tell us how everything is working. So I'm going to go ahead and go to the next slide to show you how this works. We basically label winds by the direction the winds are coming from. So if we have a wind coming from a 0 to 360 degree bearing direction, we call that a northerly wind. A wind coming from 90 degrees is a wind coming out of the east. A wind coming out of 180 degrees is coming out of the south, and a wind coming out of 270 degrees would be the west. So we like to know what direction, and we label winds by the direction the winds are coming from. because that tells us the weather that's coming towards us, and that gives us the ability to predict what the weather is going to be like in the future. I'm not interested in where the wind has already went. I want to know where the wind is coming from. So that's why we often label winds from the direction they're coming from. So if I know a wind is coming from 330 degrees, that's coming out of the northwest, and relative to Illinois, that would mean the wind is coming out of Canada. Here is an instrumentation, an aerovane that measures wind speed and direction. And often if you see a car or a van equipped with this kind of equipment here, that's telling you that you are likely to be experiencing, you're looking at a storm chaser trying to hunt down severe weather, so that might be a red flag. You might want to move in the opposite direction. That is the end of chapter 4, and the one thing I would conclude with is I would ask for you to look at airflow around highs and lows, and in particular, what is the vertical air motion? Low pressure systems pull air up and out above them, and when they pull air in, so we usually use words like low pressure systems converge air inwards, they pull the air up, and then the air in the upper atmosphere pulls out. And so we say air is converging and ascending, and that creates cloudy, wet conditions, whereas highs or anticyclones, they push air down and out. I have a couple of videos under chapter 4 that you need to see those motions, but that's why highs, by pushing air down or descending and diverging air at the surface, that's what creates clear skies, because pushing air down heats it and increases its ability to hold water vapor. And that's why pushing air down tends to produce clear skies and dry conditions, whereas lows, cyclones, by pulling air, converging air inwards and pulling it up, that tends to produce very cloudy, wet conditions. And that's why on weather maps, L's are often associated with cloudy, wet conditions, and highs are associated with dry conditions. And you need to see those videos to understand how highs and lows kind of breathe in and out, and they'll be very helpful for you with later chapters as we discuss in chapter 8. So I would strongly recommend for you to watch those videos that I post that show you air movements around anticyclones and cyclones with later material.